All right, seemingly without missing a beat. Technical issues again, but that's fine. As I look back on the video, it was approaching 50 minutes, so that's not a bad place to stop anyway. What I just showed you was the again looking at the similarities between a one-way ANOVA and repeated measures ANOVA. We saw that the sum of squares total are calculated the same way, and I was getting ready to talk about the sum of squares for the error, the within, in a one-way ANOVA, and then kind of changing it to looking at it for repeated measures ANOVA, and it crashed. So that's okay. I will tell you one thing I did is I corrected in the meantime the R. I got rid of that first column, which was driving me insane, but that's just how I roll, I guess you would say. Okay, gang, sum of squares error with or within for a one-way ANOVA. What we have to remember with this term is this is assuming different people in our groups, which leads us to what? Well, that that word. But we don't have that. We have lack of independence. So this measurement isn't different people in our group. This is actually clearly a violation of that. So again, what we're interested in, let me get my paper here. I'm get sidetracked with all this other stuff. We're interested in the variation not within the group, but within the rater. So we want to look, first of all, I think we have one rater, or we have four raters, I think we call them tutors, yeah. So we want to look at the variability within each of the raters, and the way that we would do that is this for the repeated measures. So the sum of squares for the error would be the variance for the first person times the sample size plus the variance of the scores for the second person times the sample size, and so on and so forth. Okay? And we should see clearly that this is the sum of the variances across each rater. Times the number of rates number of times they graded minus 1. Now, what's going to happen here is we want to examine across the problem. So we want to do T apply. So let me back up. There was a little bit of, I think there was some confusion. There should have been some natural confusion there the way I said it. Typically, yeah, this is not cool, guys. I explained this wrong, and let me explain what I did here. Typically, what will happen in a repeated measures ANOVA is you're going to have a subject or a person, however many we may have, and we're going to take a measurement 1 and a measurement 2, and you guys are pros at this by now. So many measurements over the length of our experiment. I messed up here because what we're looking at is, in general, it's not the person. What we're looking at is actually, in this case, the problem. So in generic terms, where we use person here, we're looking at the variation over the problem and not the person. And I chose this example for this very reason, for you guys to see that sometimes we take repeated measures at various times over something other than just a measurement on a person, and that's what we've done here in the problem. And then I almost screwed it up to where so this is going to be problem 1 and problem 2 and so on and so forth. So we're going to have 8 summations. So I hope I chose this problem for the very reason of showing you that sometimes our measurement isn't made over a person, it's made over a problem. And I almost confused myself on that one. Because it is typically. I mean, typically, I had to search pretty hard to find repeated measures that wasn't taken on a subject or a person. Anyway, gang, what we want to do here is we'd want to look at our score over the problem, and I want to look at the variance. Now I'm just wondering if I couldn't be tricky. I'll tell you what, let's just go ahead and do this. Now what I want to do next is I want to create the sum of squares error. So what I would do is I go 6.92 times, so the first problem had 4 observers, and so that would be minus 3. This is going to get really old. Type fast. 20.92. 18.25. Problem is, every time I try to type fast, I end up making a mistake. So then I get down and I'm like, well, how in the heck did that not work out? Because I know I did it right. But sometimes I get down and I find out I didn't do it right. All right, so times 3. You know, I'm thinking I may have been able to just save this as a variable and then do a sum. And I'm thinking that would have been the better way of doing this. This kind of stuff drives me insane. You know, I'd say it's driving you insane too. All right, well anyway, what we end up with here is a value of, let's just call it 1603. Okay, I'm just curious, just for the heck of it, let's just call this, say, a capital X. I just got to do this. I don't know. Will it allow me to just save it as X and then do a sum of X times 3? Wow, that would have been a lot easier, wouldn't it? All right, you live and learn. Okay, gang. Anyway, we can see that the sum of squares for the error is 1603. Now, I guess as always in this class, if there's one thing that has been consistent, is we know that our variation is a sum of 2 parts. Some of that variation is from the experimental manipulation. some of that variance is unexplained and really just a source of random fluctuation. It's so hard sometimes for me, even in the job that I do, working with very, very smart people. Some of my administrators, immediate supervisors, even, smart people. But they want to. Let's say that we do something. A few years ago, there was some debate over whether there was any advantage of using MyMathLab versus Alex versus something else. And what happened at the end of the semester, we gave a common final exam. Yeah, I'm not even going to pretend that I remember the scores. And a very, very, very smart colleague of mine says, well, that proves it. That was the best method. Well, that's pretty silly because we expect random variation. I guarantee you if we repeated this 2 hours later, we'd get something different. If we repeated it under Alex, we'd get something different with another group of students. All this tells me is for the students who made it through and actually took the final exam, that this group of students scored a little bit better than that group of students. When we seek to generalize to the methods, then we get into underlying probability distributions, things that are repeatable, things that have random fluctuation, and we go through the process of looking at p-values and so on and so forth. So there's always a source of variation that's pertained to that. Now, what we know so far is this: of the total sum of squares, which was, I don't remember, I'll have to look it up, I think it was 1706, yeah. Of this total sum of squares, which was 1706, 1603, right? Yeah, 1603 are explained by the variance in individual performance under different conditions. Now, what are our conditions, tutors? And individual performance, the scores that they give. So I'll give you kind of generic language, and we'll twist and turn it to satisfy our condition, our situation. And again, that's why I searched so hard to find a data set that wasn't across subjects, but across something different. All right, gang, the next thing that I would want to look at is my sum of squares for the model. And again, we call this the sum of squares between. And if you remember way back when, what we did here is we took the sum of the individual sample sizes and took each group mean minus the grand mean squared. So let's jump over into R and actually find that.